Okie dokie. Hi everyone, my name is Jay. Today I'll be discussing Roux-en-Y Gastric Bypass. Can everyone see this over here? Yeah? Alright. So Roux-en-Y Gastric Bypass is essentially weight loss surgery for, oh, you can see. It's essentially weight loss surgery for people with a BMI greater than 40. So, a last-ditch effort to lose weight before serious complications. When we consider Roux-en-Y and weight loss surgery in general, it's important to consider the digestive system and how that works, especially because it's linked to food intake, and that's the major cause of obesity because it gives us the calories. So when we first eat food, it passes into our esophagus and enters the stomach. From the stomach, the contents enter the small intestines, the first segment of which is the duodenum. After the duodenum, it enters the jejunum and then the ileum. So what I'm drawing here is obviously just simplified. There are a lot of other organs involved. So these three segments comprise the small intestines. And the small intestines are primarily for nutrient absorption. Nutrients. From the ileum, the contents enter the large intestine. And as I mentioned before, it's simplified. In reality, the large intestines wrap around the small intestines in a very complicated manner. But from the large intestines, stool comes out of the colon and it's been excreted. So the large intestines are primarily for water reabsorption and stool formation. When we think about the surgery itself, we're doing, the surgeon is conducting two primary perversions of the digestive system. The first one is the surgeon cuts the stomach and reduces it in size from 1,000 ml pouch to a 30 milliliter pouch. So 1,000 milliliters to 30 mils. So obviously this is a huge decrease in size, 97% decrease, and has a lot of other effects, which we'll discuss later. The second primary thing that the surgeon does is transect the small intestines, primarily the duodenum, and creates a new limb from the new stomach pouch to the jejunum. So if I redraw this, this is what the anatomy looks like after it's done. So we have our esophagus, and we have the small stomach pouch, and we have the new segment that's just been created. That's called the roux limb, also known as the alimentary limb. Then over here, we have the bypass duodenum, which is also known as the biliopancreatic limb. And the two meet at this junction, this Y-looking junction, and this is called the common limb. And the ileum and so forth proceed downwards. So if you look at this anatomy, it resembles a Y, hence Roux-en-Y, gastric bypass. When we eat food, it goes down our esophagus, enters the stomach, goes through the roux limb, down through the common limb into the large intestines. So we're bypassing a majority of the original GI tract in the form of the duodenum and the biliopancreatic limb. Right, so other bariatric procedures also exist. The second most common one is called gastric banding. So gastric banding is similar to Roux-en-Y, except we're only affecting the stomach and we're not really cutting anything. So it's a restrictive, non-invasive surgery. And in Roux-en-Y, in banding, gastric banding, the surgeon takes a silicone band and ties it around the top of the stomach and pulls. So the direct effect of this is it compresses the stomach and reduces the overall size. So similar to this, in which the size of the stomach has been decreased to 30 mils, we're just pressing, we're not actually cutting anything. So this is restrictive. Right. So when it comes to the intake of food, we also have to consider hormones. Hormones play a big role in obesity and Roux-en-Y gastric bypass. And in this, a majority of the changes involved encompass the gut-brain axis. So the gut-brain axis refers to the signaling system between the GI tract and the nervous system. And so to cover the GI portion of the gut-brain axis, let's consider L cells. L cells are in the small intestines and in the large intestines. So, and they secrete three primary hormones that are involved in the gut-brain axis, which are very impactful. The first one is called GLP-1, or glucagon-like peptide 1. The second one is called GLP-2, glucagon-like peptide 2. And the third one is called peptide double Y, or peptide YY. So what do these three hormones do? GLP-1 functions as an incretin. An incretin causes a decrease in blood glucose by increasing insulin. And I'm sure you remember from human bio and a lot of other classes that insulin is a storage hormone. It pushes glucose from the blood into the muscles and the liver as glycogen. Insulin also has been implicated in reducing food intake through a satiety mechanism. GLP-2 is released in small intestines in response to variations in nutrient availability. It also has implications in gastric motility by affecting the small intestinal peristalsis. So it can alter the rate of digestion in the small intestines by increasing or decreasing the progression of, or the frequency of the peristalsis in the muscles. And finally, we have peptide double Y. Peptide double Y acts on the arcuate nucleus, which I'll discuss in a sec, and inhibits neuropeptide Y. So neuropeptide Y has been inhibited. The normal function of neuropeptide Y is to increase the growth of fat tissue, and also raise food intake. So to increase fat tissue, you have to consume more calories. Makes sense. But since we're canceling out neuropeptide Y, we're causing the exact opposite. So we're decreasing the growth of fat tissue, and we're decreasing food intake. So I referred to the arcuate nucleus just now. The arcuate nucleus refers to a collection of neurons in the hypothalamus, which links the nervous system to the endocrine system via the pituitary gland. And as I'm sure we all know, the pituitary gland releases a variety of hormones that are linked to metabolism. So through this pathway, peptide double Y functions similar to GLP-2 in the sense that it can affect gastric motility. So there's several other brain centers or regions that are worth discussing. So this is a brain. One major region that we should discuss is the orbitofrontal cortex. The orbitofrontal cortex is responsible for reward value and decision making, so rewards. Another major one is called the amygdala. The amygdala sits in about the center, and it's responsible for the emotional response to rewards. And the last one that we'll discuss is the hypothalamus, which we have discussed already. So going back to the surgery, there are two primary stressors that we have to address. The first one is the reduction in stomach size. And the second one is this loss of the duodenum and the bypass of the biliopancreatic leg. So we've essentially just cut out this entire segment from our GI tract so that it no longer exists. And because of this loss of anatomy, a lot of bypass patients have something called dumping syndrome. And dumping syndrome is exactly what it sounds like. Continuous excretion and diarrhea after bypass surgery. So what does that happen? So dumping syndrome. Since we have lost this big chunk of anatomy, we don't have that same surface area. We don't have the same villi. In addition, just by virtue of food passing directly through the roux limb, the transit time is decreased, hence the increased excretion rate, right? So increased excretion. And so now we'll hop over to the presentation and we'll learn more. Okay. Oh, so it's on. Yeah. That would help. Yeah, nice. That helps. Yeah. Okie dokie. So like I mentioned, Like I mentioned, there are two primary stressors. The first is the reduction in stomach size. That has implications in hunger and satiety. So we'll get to that later on. The second one is a reduction in the anatomy, the loss of this entire segment. That has implications in absorption. Is it true that since we've lost a lot of surface area in the GI tract, are we going to suffer from malabsorption and other nutritional deficiencies? A common misconception about Roux-en-Y is that people lose weight from after bypass because their stomach is smaller and they just get fuller quicker because there's less volume there. The truth is there's actually a variety of hormonal changes and changes in regulation which cause a variety of other things that we'll discuss that lead to prolonged weight loss after bypass compared to just dieting. So this is what it looks like in figure form. Notice the Y, the small gastric pouch. The bypass duodenum is just functioning as a pathway for digestive juice. So this figure shows us that we have increased enteroglucagon in patients at various time points. What the researchers did was they looked at 6 patients before and after gastric bypass, and they measured different hormone levels in their blood. So one thing they found was enteroglucagon levels. The hormones we discussed, GLP-1, 2, and peptide double Y, are enteroglucagons. Increased presence of enteroglucagons shows that there's increased L cell activity, that they're more active after Roux-en-Y gastric bypass. So since L cells are more active, does that mean these other hormones, such as PYY, GLP-1, GLP-2, are also increased? We find that to be true. There's a general upward trend after bypass in GLP-1 and PYY. And they assess this using the blood assays, like I mentioned. They also asked the same subjects about hunger and satiety. So they asked them, how hungry do you feel and how satiated do you feel? So it's worthwhile to discuss, number one, what's a visual analog scale? And number two, what's the difference between hunger and satiety? The two are different. So what's a visual analog scale? It's essentially a response scale used by questionnaires to gain input on subjective attitudes about things you can't really measure directly. So in this case, they ask, how hungry do you feel after intaking a 420 calorie meal, liquid mixed meal, so like Ensure, which is like a meal replacement shake you can buy. And they asked this at several time points after they ingested the liquid meal. And they did the same for satiety. And there are very striking differences in the response. So before surgery, the response hovers around 70, 60, 70. After 6 months after bypass, it hovers around 20. So massive decrease in hunger ratings and massive increase in satiety. For satiety, after 180 minutes after the meal, pre-op patients report about like a 25-ish rating. 6 months after, it's about 75. So we have decreased hunger, we have increased satiety. Does this mean that bypass patients are eating less as a result? Typically when people gain weight, they may not be hungry, but they are not satiated. Oh, I forgot to mention the difference. Hunger is a biological signal that tells you need calories that you need to eat because of a biological need. Satiety is just how full you feel. Are you satisfied? So people can not be hungry, they won't need calories, but they'll still feel unsatisfied, so they'll eat more. So this is where obesity comes in. So this study looked at the impact of the increased hormone levels, especially particularly PYY and GLP-1 on food intake. So this was in fasted lean rats or mice, and they injected varying levels of peptide double Y and GLP-1 to glean, is there any difference in food intake? And there is a dose response in the GLP-1. You notice that food intake decreases in a downward fashion for both, but especially GLP-1. After conducting this study, they reasoned or questioned, is it possible that the two can work together to produce a synergistic effect? And they found that to be true. Once they combined GLP-1 and peptide double Y, they found over a 90% decrease compared to the saline. So combining these two hormones produces a severe decrease in food intake. This is especially interesting because the rats have been starving for 20 hours. So you'd expect them to eat more, not much less, especially 90% less. They also repeated the study in humans. So can this be applied to humans also? So they took several healthy human volunteers and they sent them to a free lunch buffet 4 different times, 3 days apart. The first day, there was a saline injection. It was the control, and they measured how much food they ate. So they measured the food before and after their meal. The meal was composed of vegetables, curry, rice, sweets. And they found that patients on average consumed about 4,000 kilojoules of food in the saline group. Fast forward to on the second occasion, they had just a GLP injection. Third time, they had a peptide Y injection. And the last time, they co-administered both peptides simultaneously. And they found that there was a 27% reduction in the total calories taken. To reference back to the 4,000 calories consumed, they only consumed 3,000 calories. Keep in mind this is during one meal, so it's still a lot, but severe decrease of about 1,700 calories, which is over half of a pound if you just measure it in terms of energy to pound conversion of fat or muscle. So in this study, they reasoned, what's the reason why there's a massive synergistic decrease in energy intake? And they thought that perhaps there's a connection to archaeonucleus activation because there's the role of peptide Y. So peptide Y decreased energy intake more than GLP-1, so they figured there's probably a higher chance that peptide Y is involved. And so they couldn't measure changes in archaeonucleus activation in humans, but they did do it in the mice. So they took the mice and they took the brains out after injecting them with the 2 different peptides, and they sectioned them. Then they stained for C-FOS positive nuclei. So FOS or FOS is just a marker for archaeonucleus activation. And they found a region, and they compared the regions from all the different peptide administrations and tried to determine the counts. So a higher count means greater archaeonucleus activation. And they found that the 2 synergistically increase archaeonucleus activation by 85%. What's more interesting is the peptide Y and GLP-1 concentrations that they used. So here they've noticed that it's almost identical to saline. The reason behind this was they found the bare minimum amount of peptide Y and GLP-1 needed to cause a response, and they combined the same concentrations together to see if there is an effect. And there is a synergy because of the 85% increase in activation in the archaeonucleus. So we know there's hypothalamic activation. Is it possible that there's other brain reward, or is there other brain activation occurring? And this study found that they subjected several patients from Roux-en-Y bypass, gastric banding, and BMI matched control groups. They put them in an fMRI machine and showed them different foods, and they measured changes in brain activity. They specifically measured BOLD activation. BOLD refers to blood oxygen level defense, and that's just a marker for neuronal activation. So I'm not going to go into all 5 of these. They measured 5 regions of interest. Only 2 of these were significant and caused the most change in brain reward. And the 2 are the amygdala and the orbitofrontal cortex. And let's talk about those now. So the first one is the orbitofrontal cortex. And both, you guys see there's a massive decrease in Roux-en-Y in activation of the brain after Roux-en-Y, especially compared to band. So if you want to get some kind of gastric bypass, get Roux-en-Y, not gastric banding, because Roux-en-Y is more effective in terms of brain reward. What this means is when people saw these different foods, they had less neuronal activation and were less rewarded by looking at the food. It's especially interesting because they did high-calorie foods, low-calorie foods, and just foods in general. They also controlled for objects. So they would show like household items, blurred objects, just to see differences and normalize for that. They also asked the same subjects just questions about food appeal. Does this food look appealing to you? So they asked about high-calorie foods, low-calorie foods. The same things as in the previous MRI study. So it's the same study, but just different components. And this one, Roux-en-Y patients had severely decreased food appeal across the board, but especially amongst chocolate, which is interesting. So just fun fact. So now, we've covered a reduction in stomach, and we see that there's a change in hormonal activation or hormonal regulation, which causes a change in brain reward, brain activation, and that results in food intake. Now let's look at the absorption component. Is there malabsorption as we previously thought, or as common sense would dictate, because we're missing a large piece of anatomy? So in this study, the researchers took mice and they resectioned the intestines, meaning they took the intestines, cut a segment out, measured GLP-2 levels, and they compared the two. And what they found was as the mucosal surface area increases, GLP-2 decreases. And so the significance of that is that as surface area decreases, GLP-2 increases. So when we've cut, as soon as we conduct the surgery, GLP-2 should be higher. So this begs the question, is there an adaptation outright right after that? And we learned that there is an increase in villus height as time goes on. So this was over 28 days. We find that the resected intestines have an increase in villus height, in villi height as time goes on, 7%. Control had a minus 0.6%, but that's you can have that reasonable chance. So that's a possible direct adaptation right after surgery. Next, they tried to compare the GLP-2 to another adaptation. Is it possible that the crypt cells are increasing in number to combat this decrease in surface area? And what they found was there's an increase in cell proliferation. They measured this by using two antibodies. The first one is a primary monoclonal antibody called Roux-en-Y. It selectively is incorporated in crypt cells that are undergoing the S phase. So the second antibody they used was anti-mouse IgG, and that just tagged cells that had incorporated the S phase one. And so they found that GLP-2 levels correlated with increased Roux-en-Y incorporation. So more cell proliferation correlates with greater GLP-2. That's 28 days post-operation. So the previous this study repeated had the same results as the last study in terms of crypt cell proliferation. They also looked at apoptosis. Are these crypt cells dying quicker because they're being more frequently used, or just because they're undergoing they're being put under more stress? They did a caspase assay to see the level of apoptosis during in the villi or in the crypt cells. So they found a ratio of the cells undergoing apoptosis and compared it to the total number of crypt cells overall. And they found that there was a decrease after Roux-en-Y bypass in the apoptotic account. They didn't really find a difference in the biliary pancreatic limb, but that makes sense because we're bypassing it. There's no need to really change anything in terms of cell proliferation or apoptosis. We could hypothesize that maybe that there should be greater apoptosis, but the study didn't really delve into that because this more apoptosis because it's not being used. Yeah, so we have this shows that crypt cells are not only increasing in number, but they're more resilient. They're living longer, and possibly they have a greater, they have more absorptive capabilities because they're living longer and they're needed. And so they tried to determine that in this next study in this study, they essentially took human subjects and infused them with a leucine marker via the blood. They then gave them a test meal, which was composed of an intrinsically labeled caseinate with leucine. So they just found the rate of absorption of leucine consumed orally, and found that the rate of absorption of leucine into the blood increased threefold 3 months after bypass than 2 weeks before bypass. They also found that the time to peak was 108 minutes faster than original. So this shows that there's an accelerated systemic uptake of leucine after Roux-en-Y. This is especially interesting because amino acid absorption isn't really being affected negatively despite this loss of anatomy. In fact, it's more efficient and it's just better at absorbing. This study relates back to the dumping syndrome. So we've gone over, the increase in villi height and other intestinal changes. This goes over, how does this impact the rate of, how does this impact motility? Because we've been elevating GLP-2 and peptide double Y, which are implicated in gastric motility. So this study they took rats or mice, and they gave them a pre-weighed 2-gram food pellet. And after that, they gave them 2 hours to eat. After that, they decapitated them, took out the stomach, and measured the food contents. Then they measured how much had been, how much was present, and they compared how much they ate. So in the end, they learned how much had passed through the system in terms of excrement or stool. And they found that Roux-en-Y mice had decreased percentage of emptying. For the transit time, instead of giving them food, they force-fed them something called Evans blue solution. That's just a marker to determine how fast the intestines are, how fast motility is. So again, this time they gave them a half hour after force feeding, decapitated the heads, took out the stomach, or took out the intestines, and then measured how far along had the blue solution progressed. And they found that in the Roux-en-Y mice, it had gone almost a little more than half as far as control. So this shows that there is a decreased gastric emptying rate, slower motility. And this relates to the dumping syndrome because it's an adaptation to dumping. Instead of the normal rate of digestion, it's been slowed down so that people weren't excreting more frequently. So in conclusion, like I mentioned before, the misconception is people that undergo bypass lose a lot of weight because of the reduction in stomach size. The reality is there are a ton of changes hormonally and through other absorption mechanisms which promote weight loss that couldn't be sustained otherwise using just diet alone. So that's why in Roux-en-Y, after 20 years, there's an average weight loss of 25%. In gastric banding, it's only 14%. And for dieting, a lot of people don't really keep it off. They tend to. And that's it. Thank you.